We are looking at maximum depth of binary tree today. Again, we have moved on to the binary tree section here. Also, hey, welcome in, folks. Yes, maximum depth of binary tree, second binary tree problem here. We talked about some basics of trees yesterday, and we'll talk about some more today. So let's take a look. Okay, so our prompt, given the root of a binary tree, we want to return its depth. And they define it for us here. The depth of a binary tree is defined as the number of nodes along the longest path from the root node down to the farthest leaf node. So we want to know how many steps can you take basically until you get to a leaf node. So we can tell pretty easily, because we've got the whole tree in front of us here, that the maximum depth here is 3. And I actually lied a little bit, but I said how many steps from the top to the bottom. It's actually how many nodes along that path. So in this case, it's 3 because you got the root node. You can go down one layer here, and then go down another layer, and that's 3. We want the deepest possible path here. So even though there's a path of 2 here, we're going to return 3 because the deepest possible is 3 nodes long. Again, the way that this is structured is that we don't have the whole tree given to us in memory. If we did, that'd be really easy to figure out. Instead, we're just given the root node, and we have to use a programmatic approach to go down the tree until we get to the deepest possible place. Okay, and yeah, so that's it. Again, we're just going to be given a root. We got to find out how to traverse the tree and get the information. They give us one edge case example here, which is that if we're given a none node as the root, we can just return 0 because there are no nodes in the path at all. Okay, speaking of which, the constraints, the number of nodes will be between 0 and 100. The values, which we're not going to manipulate, will be between negative 100 and positive 100. Okay, so we did a recursive solution yesterday for invert binary tree. We're going to do something very similar today, so let's take a look. We'll even use their example here. Open up a new page here. So let's say we've got a tree that looks like this. Again, at any given time, the only thing that we're aware of is the node that we're given, and then we can follow its left and right pointers. We can get its value as well, but the value is not super helpful for us here. Okay, so let's say we've got this tree here. We got like 1, 2, 3. And then I'll just put like a, well, maybe we'll do a little bit more than the example. I'll put a 4 here. And I'll put a 5 right here, maybe. Okay. Great. So if we decide to approach this recursively, the question that we're trying to ask is like, what is the maximum depth beginning from this node, right? I think it's actually somewhat helpful to start from the base case this time. So when would we know what the maximum depth is? Well, if we have one of two situations, again, we tried to capture something similar yesterday. If we reach a none node, so there's like nones kind of attached at the bottom here. If you reach a none node, like they told us in that constraint example, the height is just automatically 0, right? So that's actually quite a helpful base case. Okay, and there's nones all the way through here. So that's a good base case to start from. If you reach a none node, then the height is 0. Now, for any like random node in this tree, so if we take a step up from there, for example, let's take a look at maybe this subtree right here. If we're just asking ourselves, like, what is the height of node 5 right there? We know that it's 1, and one way that we can think about this, well, if you're approaching this problem from scratch, you're either thinking, well, it's 1 because it has 2 none nodes, or maybe it's 1 because that's a base case. Like, there's 2 ways you could approach that, right? So let's take this one step further. Let's now look at a slightly wider subtree that looks like this. Oh, that's not the shape I wanted, but it'll do. So now if we look at a slightly more involved subtree, this is so ugly anyways. Anyways, the point here is if we now ask ourselves, like, what is the height of this subtree? Well, you can count it out by saying, let's go down the path, and we find out that it's 2. But if we want to think about this recursively, we've got to think about, like, could I extract that information just by thinking about what is true from the left side and what is true from the right side? Okay, so let's do a little bit more labeling here. These guys have a height of 0, height of 0. This guy had a height of 1. This guy had a height of 0. And we know by looking at it that this node right here has a height of 2, right? But how could we figure that out? By using just information from the left and the right subtree. Well, if you know what the heights on the left, or the depth on the left and the depth on the right is, then the node that you're currently looking at is just going to be one more than the bigger of those two, right? So if the right subtree has a height of 1, the left subtree has a height of 0, pick the bigger one and then add 1 to it, and you get the height of the current node, right? So similarly with the next layer up from here, right? If we know that the left subtree has a height of 2, so we're basically feeding this information back up here. If we know that the left subtree has a height of 2, the right subtree has a height of 0, and I keep saying height when I really mean depth, then we know that this node has a height of whichever one's bigger, which is 2 plus 1 more is 3. So if we start from the base case and we think about just how to build it up, it becomes pretty clear that all we need to do is find the height on the left and the right, the depth on the left and the right, and then add 1 to that, and that's the new height, right? Okay, so same thing with, so we eventually want to know the height of this guy or the depth of this guy. We now know what the depth on the right is. Now we can figure out the depth on the left. Well, these guys are our base case of 0. We pick the bigger of those two, which is still 0, and add 1 to it to get 1. And then finally for the root node, left max depth is 1, right max depth is 3. The bigger of those is 3, and we add 1 to it to get 4. And that gets returned to the calling function here. Okay, now the way that we did this was we went as deep as possible in one direction. Deep? One direction? We went deep into one direction. And this is what we refer to as a depth-first search. Okay? This means kind of explore one path until you get to the very end of it. Right, and it doesn't have to be a search like in the sense that we're not looking for a particular node here. We might call this a depth-first traversal. So it doesn't have to be a search. More of a traversal here. Anyways, depth-first means if you start exploring a path, continue until you can no longer explore it. And this is as opposed to breadth-first traversal. So let me see. Well, yeah, maybe, I don't know how messy this is going to get. I'm going to try and write on top of this. Breadth-first traversal would be if we went basically one layer at a time. We would say, okay, get everything in this layer, right, which is just when we start the root, and then explore all of its children, so all of the children that come next, right? This would be layer 2, and then now explore all of the children that come next. Well, these guys are none, but this one actually continues, so we have one more node in this layer. Get all of its children, well, this is none, and then we would go down here, so there's one more layer there, and then finally, when we get to this point, there's no more paths for us to explore, and so this is another way that we could do it, and this would be a breadth-first search, where we kind of complete each layer before moving on to the next. Okay, and I keep saying search, it's not really a search, it's a breadth-first traversal. Okay. Between these two, for this particular problem, depth first is a lot easier, but I think we have time to do both. So we'll do the depth first search, and then we will talk about how we can do it as breadth first. So both of these, they're meant to keep going until there are no more paths to explore. Breadth first does it layer by layer. Depth first completely explores one path, and then backs up and explores all of the paths that we missed the first time, basically. All right. In either case here, we're going to end up returning to the calling function the total height. So with the depth first, we return that height by getting the max height on the left, max height on the right, and then adding 1 to it. With breadth first, since we go layer by layer, we can basically say like, hey, for every time that we actually have a node, just increase the layer count until you run out of things to return. And this will also get us the same result. Notice we don't have to do breadth first recursively. We can just set up some system for continuously like looping until we run out of nodes. Depth first, we pretty much have to use recursion or else implement our own stack to do the recursion. Okay, so yeah. Again, the way the depth first method here that uses recursion, we're answering a fundamental question, which is like if we could make sure that this was already done for the left and the right trees, which we rely on recursion for that, could we do this for just the node we're looking at, right? So same overall process where we say like this is actually something we could repeat for every single node, and then we could build up the answer. And then the last thing we do is just identify a base case. So let's give a shot to the code here. And if anybody has questions, as usual, let me know, but I'm gonna go for it here. So if we want to know the height of the node that we're currently looking at, find the height of, and again, the depth of the left node, find the depth of the right node, okay? And in fact, what we need to do here is pick the bigger of those two. So we can say max of these and add 1 to it. And that's the height of the depth of the current node, right? So we got that. And then our base case is, hey, if we reach a none node, you can just go ahead and return 0 automatically. So if not root, return 0. And then assuming we didn't reach the base case, go ahead and repeat this process on the left, repeat this process on the right. Whichever one gave you the bigger depth, add 1 to it and return. And I think that's it, which is crazy. I can't believe this is like a 2-liner basically. Wow. And I bet we could make this a 1-liner actually. Return 0 if not root, else that. This is not a good practice to be in, but I think it works. Feels good. I haven't actually tried to do that in a while. So yeah, 1-liner. I wonder if there's like a. Yeah. Anyways, probably a better way you could do this, even that would be shorter, but this one works just fine. Okay, so that's the depth first method. Again, I think in terms of showing like what's actually happening here, this is a little bit better. We have a base case, which is, hey, there's certain situations where we just know what the height is. We have no calculations we need to make. Otherwise, we can describe the current node's height as the bigger of its 2 children plus 1, right? And it's a little bit hand wavy on purpose because this part is accomplished by doing the recursion. So we don't know what it is, but we're saying we could figure it out if we just kept going on that side or in that direction. Okay, yeah, we definitely do have time for breadth first search. So let me know if you have questions on depth first search, and I'm gonna start on breadth first traversal. Right here. So I'm gonna say depth equals 0, because when we start, like, there's nothing, right? In order to do the breadth first search, we're going to use a queue here. Now, we haven't really talked about queues. It doesn't really matter that it's a queue here. It has the nature of a queue because what we're going to do is the first nodes to come in are going to be the first nodes to come out. So if you know about queues, that's a helpful thing to know. But in this case, all we're basically going to do is keep track of like the current nodes in this layer, grab all of their children. Ooh, let me say that differently. Keep track of all the current nodes in this layer, Now I'm going to say capture all the children, and that's worse too. We'll keep track of all of the next layer's nodes and then clear out the old layer. So yeah, the overall process here is like get all the nodes in a layer, use that information to get all the nodes in the next layer, and then clear out the old ones. So how can we do this efficiently? We'll probably talk about this more in depth because there's literally a problem that like the problem is binary, like level order traversal. But anyways, here's how we can do it. We can say node queue equals empty list. And just so we can capture that situation where there's not a root, we can say if root node queue dot append root. So we're going to add the root because that's the first layer, right? In. And then here's where it gets a little bit funky. We can say while node queue. So as long as there is something in the queue, we'll keep doing this. And this also means if there was never a root, then we'll just return 0, which was the original depth, right? Okay, so while node queue, what are we gonna do? This is the like idiom that I've gotten accustomed to. There might be a different way to do this that's better, but I find that this is very easy to follow. I'm gonna say num old nodes. So first I'm gonna say, hey, what's the number of nodes that we need to process? And originally it's the length of node queue, right? So when we start it's 1, in the next layer maybe it's 2 or whatever it may be. Okay, now we need this information because what we're gonna do is we're gonna iterate just over the old nodes first. So you could also do this by having like an old node queue and a new node queue. Just to save on space, we'll do it this way. So num old nodes is this. And then we can say for I in range num old nodes, we're going to go ahead and add on that node's children. So actually, if node queue I dot left, so if there is a left node, we'll add it into the node queue. Okay, and then exact same thing on the right. So I'll just copy paste this. Oh, why does it do that? Anyways, if there's a right node, we'll append the right node. Okay, and if not, then if it has no children, then there's nothing else to add. There's nothing that this node is contributing to the next layer, so we're good on that. Okay, and now that we're done adding all of the new nodes, what we can do is we can say node queue equals, and we can just slice it. Basically what we're going to say is all I want is from where the new nodes start to the end, right? So we can say num old nodes colon. And we can put a -1 here if we want, but it works this way. So this says go ahead and slice off all of the old nodes, and then now we can begin processing the next layer, which means we can add 1 to the depth. Okay, and eventually there's no more nodes that get added. We've gotten to the last layer, we exit this loop, and we return, ooh, not 0, but depth. Okay. I think this does it, but I guess we'll run it and see. Yay. Okay, and the nice thing about this is notice I never have to recall the current function, so I'm not dealing with like stack recursion. We just run this while loop until we run out of like nodes. And in terms of like overall time complexity, this is not worse than depth first search because all of the operations we do here, like the append, for example, is O of 1, and then the list slice is actually also O of 1. Normally removing from the front is like not desirable, but since the only thing we ever do is slice off all of the front nodes, this is actually just O of 1. Ooh, actually, is it? I think these all get copied one by one. So it is O of n, but we don't repeat it. Like every node gets added and removed from the queue exactly once. So we're not contributing to the time complexity here. This is going to be like O of 2n for the entire process. So yeah, and you could improve this even by, so earlier I mentioned like you could do like an old node list and a new node list. If you did that, then when you transferred you could just make the like pointers move to different places. So actually, that would probably be more efficient because we don't have to do any copying from the slicing, right? Oh yeah, well you missed depth first traversal, you missed breadth first traversal part 1. Let's see if we can do this because we got a little time. Let's see if we can do this and see if it's improved time complexity if we do like old nodes and new nodes. Okay, so this is going to be old nodes dot append root. Okay, and then what do we want to do? We want to say while old nodes, basically. Okay, so same process as before. We're going to say for, well, this is kind of nice too. We can say for node in old nodes, new nodes dot append. Oh, well, again, we have to do some checking here. If node dot left, new nodes dot append node dot left, and if node dot right, new nodes dot append node dot right. Okay, and then once we're done with that, what are we gonna do? Well, at this point, we can throw away the old nodes. And new nodes is just an empty list, and the depth increases by 1. So actually, this is a little bit better, huh? Because this doesn't require us to like copy anything over. We can just point old nodes at a different place, and then the empty list is O of 1 to construct. And so I think this is actually better in terms of performance. Let's just make sure it actually works. Great. Okay, well, I learned something new today. I never thought about handling it that way. And it's a little bit nicer because we don't have to like do any like weird slicing index stuff. I rather like this approach. So the simplest one, probably our depth first search that we did at the beginning. That's literally one-linerable if we want. But yeah, again, interviews, they love to see that you've got a couple approaches under your belt that you can figure out. Let's just compare the runtimes real quick. This was 0.7 for the depth first. 0.8 for the breadth first. So largely not, certainly same time complexity here. But the breadth first does take a little bit longer. Probably just because we're doing a lot more like list manipulation and stuff here. Yeah. Well, that's that. We ended a tiny bit early, but good place to be in. What's tomorrow's problem? Ooh, this one's kind of a fun one too. Anyways, that's what we got for tonight. Oh yeah, you're right. Not tomorrow, but Monday's problem. Okay, well, thanks for tuning in, friends, and see you Monday.